Hello and welcome back to Dozzy's Television Workshop. Today we're doing a video on test equipment, and it came out of a comment left on my website. So on the 4th of May I posted an article about the future, and I was weighing up YouTube versus written on the internet and which way I was going to go. And I think I'm going to go and do both if I can. If I can keep it up, that's the way it's going to happen. I thoroughly enjoyed making the videos recently. We've had great response, and it's great to be here. But I do miss writing on the website. But I'm going to try and do bits of both. Certainly project stuff, it's more going to be there. Demonstrating projects, it's more going to be there. Anyway, we had a few lovely comments. It was 5 comments. A lot of people saying they'd rather read, which is good, because I'd rather write. But I think the information comes across slightly better on video on some occasions. So I'm going to try and get a happy medium in there. Anyway, there was a lovely comment. Anonymous wrote on the 21st of May, whatever path you end up taking, I'm sure it'll be interesting. With so much interest in the resurrection and reuse of ancient kit, there's a lot of demand. Retro's big, isn't it? One idea is to have a mini series of videos and posts on the use of test equipment. It's often just assumed that people know how to get the best out of what they have, and I suspect it's not true. Do you know, it's interesting you say that, because I'm actually filming this bit after I've done that bit, and I've just realised there's a function on one of my multimeters that I'd forgotten about years ago, but there it is. Yeah, so there's a lot to go through on test equipment. I think this video is running into something like an hour long already, but I do cover what I've got here and what I couldn't live without. And I suspect there's probably only 1 or 2 instruments I really couldn't live without. Anyway, here it is. Enjoy. First thing I've got to talk about, I've got a few components here. I've got a transistor, a diode, a capacitor and a resistor. That we can test those, and I can show you what goes on there. The first thing we've got to discuss, isn't it? It's the multimeter. There it is. This is my Fluke 77. In 1988, this cost me £108. My car at the time didn't cost me £108, so this was quite an investment for a farty student at the time. It has been the cheapest test instrument I have ever bought. It is undeniably, superbly reliable. And I remember speaking to one of the lecturers at college, and lecturers at college at that time, they had sort of come out of industry. And yeah, he said there are 3 types of multimeter to consider, Mr. Dawes. And he said there are 3 brands: Fluke, Fluke and Fluke. So I bought myself a Fluke 77. Best purchase of my life, I think. It has been superb. So there we are. A little while later in life, I thought this was going faulty. It wasn't. It was, I think it was a lead or something. And somebody offered me a Fluke 87. Which is its sort of later bigger brother. This is a Mark V. Look, 77 is not even a Mark 1. And it's a great meter. Fluke 87 Mark V. It's okay. It's not my favourite. It's this one. And I'll tell you for why. Let's just... I'll come back to why. So, we've got our meter. Get the rubber holster with the stand as an extra. If it is extra. I think it came with this one. I think I haggled with somebody to do a bit of a deal for a student, and they get it through in the case. I seem to remember that's the case. Runs on a square 999 PP3 9-volt battery. Measures AC volts. Give it a second to start up. Measures AC volts. I think it'll cope with 750 volts AC. 1000 volts DC. Auto ranging, by the way. This is a millivolts range, so anything up to 300 millivolts. Ohms, so useful for testing resistors. and other things. 5 meg ohm there showing is me. In fact, can we see that on that? We can. Good. Okay, there's a diode test range. Now the diode test range, this is why I like this meter. The diode test range is also continuity. So we get continuity, we get that lovely beep. Just switch that around. This meter, if I go to the ohms and beep range, I get nothing. I get ohms, it's reading fine on ohms, but I don't get the beep. You have to push the, no, you push that button, I think. Oh, now I've done it, haven't I? Push that button to get beep. The beep's a lot better, but extra button push. Drives me mad. Don't want an extra button push. And I sort of know how this meter works without even having to think about it. So ohms, yep. Here's a 1k resistor. So if I put my probes across there, we should get somewhere near to 1k. 1000 ohms, 1001 ohms. Brilliant. One thing to note when you're measuring resistors, if you're measuring them in circuit, obviously you're measuring the entire circuit that these two probes are seeing. So sometimes you don't get a value you want. Just lift one end and measure it across there. Also, if you're measuring them just in your hand, you know, you need to take into account that probably, what am I there? 1.6, 1.7 meg ohms with dry skin. And I'm a bit sweaty. I am down to, there we go, 150k or so. So if you measure a resistor like that, and it's a bigger value than you are, or even if it's, yeah, you're going to get a lower value. There you go, look, I'm down to 996 ohms without me touching it, 1000 ohms. So that's an effect because I'm in the circuit as well. Just worth considering. Now, the diode option on your meter, very good. So we connect the diode up, and as you can see there, it's showing 0.527. That's volts drop in millivolts. I wonder if I'm affecting that actually, not by much. So that's volts drop in millivolts. So our diode is conducting, but we've got about half a volt disappearing across it. If I turn it round, it's open circuit. That diode's good. It is a good diode. There it is. One way and the other way, it's open. If you've got a diode that measures open circuit in both directions, it's a good chance it's no good anymore. And if it's short circuit in both directions, it's had it. Those are the sort of two methods of failure. You can get leaky diodes. And then when you may get a reading in that reverse direction where you'd normally see open, you may get some leakage reading. But this is a good basic test. I'll come back to capacitance in a minute. We can't really test capacitance on our meter because if we do, we'll just get a resistance reading that sort of changes as the capacitor charges up. Yeah, not ideal. So this meter will not read a capacitor properly. Back to diodes, we can of course use our diode setting to check a transistor. An ordinary bipolar transistor, such as this one here, this is a 2N3773 RSA, whatever that is. So with this sort of power transistor, even though it even applies to the small BC547s and things like that, you can test these in that manner. So a transistor, if you think about it, we've got our base, collector and emitter. We've effectively got two diodes welded together at the base. I'll stick a little diagram up over the top of there. It'll appear here somewhere. So if we can measure two diodes within our transistor, it should be a good one. Maybe a good one. So can we measure a diode in that direction? No, we can't. I happen to know the case on this is always a collector. So the first beat we get is going to be our base here. There it is. There's our base. And we've got a volts drop there of 0.449, 0.450, sorry. So about 0.4 of a volt. And between base and the emitter here, a similar sort of voltage. So we've got two diodes in there, and it shouldn't measure any other way around. If it does, check your spec. Sometimes there's an extra diode in a transistor. If you get measures any which way around, or you've got any really low readings, you know, short circuit type, that sort of reading, that transistor's cooked. Again, really simple basic test. MOSFET's not so easy because the meter, the voltage used on the sense of the meter, it's quite likely to switch one on anyway. And some of these FETs measure very, very low. So yeah, you have to use it with caution. But for your ordinary bipolar silicon transistors, just the ticket. So that's the dear old Fluke 77. If we want to measure a voltage, for example, we just click it round to volts. In fact, let's have a 1.5 volt battery here. This is a brand new one. So let's just see what that measures like. Just pop the positive probe on there, and there we go, 1.619 volts. And it should read the same around the other way, 0.620 minus. So yeah, do obviously make sure if you're measuring a voltage that you're measuring it the right way around. Got a black probe on the positive tip here, and the meter is seeing 1.6 volts plus 1.6 volts minus plus. So don't get that round the wrong way. The beauty of it is, of course, is you won't damage the meter by reversing the probes. Now, when I started in college, where is it? Oh, it's over here. Everybody sort of had these things, and we were taught how to use those. This is an universal Avometer 8. You'll find these at car boot sales everywhere. Some people love them. I find it's okay. I can read it all. Works really well. It's nice and accurate under normal circumstances anyway. It's got a cutout. If you do cross the meter, the leads around the wrong way though, it doesn't go negative, so you can damage its very sensitive mechanical movement. Also, these have an impedance of 20,000 ohms per volt. So if you're measuring a volt, it's 20,000. If you're measuring 2 volts, it's 40,000, etc. It's not a constant load on the circuit. Your digital meter presents a constant load of about 10 megohms. Certainly a Fluke is 10 megohms. So different things. The older equipment, things like that Philips telly we did the other week, the manual will specify probably a 10k or 20k per volt instrument to measure those voltages. Those are the voltages they suggest you should get when the instrument is loading the circuit down slightly. This will read a higher voltage because this presents a higher load to the circuit, something to keep in mind. Also, when measuring voltage, if you've built the Geiger counter project that we did on the website years ago, you'll notice that you can't actually set the HT level on the Geiger tube by measuring it at the tube, because there's 6 million ohms in between the supply and the tube. And of course, this is 1 million ohms, so it basically shunts most of the voltage away. So this reads very, very low, despite the fact you've got 500 or 600 volts there. This, I can't remember what it reads, 90 or something. But yeah, it reads a lot lower because it's literally loading the circuit down. So that's the Avometer. Now, Fluke meters, very, very popular with us Brits and the Americans. On the continent, I understand this is very popular. This is a Metra hit. It is made by, where is it? Grossen and Metrawatt GmbH, Germany. Superb instrument. And if I just switch it on here, there we go. You will notice it has a lot of digits. So it's capable of measuring in a bit more accuracy than our ordinary Flukes. So yeah. The other thing, I will compare and contrast the 3 meters. If I want to measure current on all meters, I've got to move my positive probe across. In this meter, if I want to measure up to 300 milliamps, I move my red lead into there. If I want to measure up to 10 amps, I move my red lead into there. And you insert the meter in series with your circuit, not in parallel with it. That's that. With this meter, same thing, I must move it over. If I yeah, with this one, we move it round to amps. It defaults to AC, which drives me mad, and we have to push DC somewhere. Where's that? I've got the wrong glasses on. AC, DC. This one is DC and AC are separate windings. Another reason I don't like this instrument so much. But it will if I then go to measure 10 amps, for example, I then go back to voltage, it comes up and it warns me my leads are wrong. Because if I actually try to measure a voltage on that, I'm going to draw an awful lot of current through here and blow the fuse, possibly damage the meter. So it does warn me. This one doesn't. This runs the risk of me blowing the fuse, possibly damaging the meter. Metro hit, even better idea. Here, you can see I can't physically insert my meter probes into the milliamps and amps socket. I'm in these two at the moment. So if I move it around to milliamps, watch what happens. The little window moves across and uncovers it. If I move over to amps, how clever is that? You physically can't get it wrong. If you've already got a meter probe in there and you try and move it across, you can't because it's mechanically jamming it. It's a brilliant design. It really is. I don't use it enough. I've had it for years, but it was... yeah, it came at a sensible money, so I treated it. It's also got a data logger on it that I don't think I've ever used. Good instrument. If you see one at inexpensive prices, pick one up. There is a function that this meter has that neither the MetroHit or the 77 have, and that is, it is actually capable of reading a capacitance. So we push the yellow function key to give us capacitance. There's a few nanofarads. That's probably in the capacitance of the leads. But if we connect this onto this capacitor, 703, 702 microfarads. I don't find it particularly accurate, but this is a 680 microfarad capacitor. It's brand fire new. So yeah, that's probably about right. There we are. So our multimeter, just... you know, get the best one you can afford. The unit ones, I understand, are very well thought of. I see a lot of people use those on YouTube. Big Clive's got some kit that seems all right. But these are the ones I bought, you know, 40 years ago. It's been through the mill with me. Look at the state of it, really. But it's been a really good friend, and I like it a lot. Don't mind this one. I ought to use this one more because this is a thoroughly decent instrument. There we have it. So those... you know, and I'm just trying to sort of think, what are the percentages of faults we can repair with just a multimeter? And I'm thinking, you know, you're probably into 80 or 90% just with a multimeter. Fix, you know, faults on electrical faults on cars, all manner of stuff. It does, you know, you need to develop your own sort of fault finding scheme, but yeah, a really useful piece of equipment. You know, if you want to analyze logic levels, you can do it with voltage. A bit limited, I suppose, if you're trying to see data patterns. You can't really do that, but yeah, you know, a lot of faults you can fix with just a multimeter, certainly for hi-fi repairs and things like that. Get yourself a good one. There we are. Right, that's sort of dealt with a multimeter a bit. Now, I think we ought to have a word, really, about oscilloscopes. Let me just switch on my oscilloscope camera. And I'll show you my oscilloscope that I have had for about 1,000,000 years. You'll often see it with its display on the camera, on my videos, and photographs taken on the website. One moment, the scope cam is, oh, it's starting. We're in with some luck. There it is. Right, let's just hit record. Okay, so that's my Tektronix TDS 2014. It was second-hand. It was quite a bit of money. It's been superbly reliable. It's never given me a moment's problem. So what does an oscilloscope do? Well, we've got 4 channels of input. So we've got 4 methods of measuring voltage here. Channels 1, 2, 3, and 4. To be quite honest with you, I've used 2 channels often, 1 channel very often, 2 channels often, 3 channels rarely. I can't ever think of a time when I've had 4 channels displayed at once. So there we go. You can get many channels. You get logic analyzers, basically the same thing, but with, I don't know, 16 channels or 16, or whatever. So an oscilloscope, what it essentially does, this is the speed here on the left. And as I turn it down, there you go. You can sort of see that trace going across there. So it plots a graph of time against voltage. So if I just connect channel 1 here, I'm going to connect it to another piece of test gear. I was going so slow we couldn't see it. Right, so all it's doing is plotting voltage against time. So this is time moving along here, and here is our output from our signal generator. It's a sine wave. There it is. It's quite nice because it gives us a little bit more information down here. It tells us it's a kilohertz. This is not particularly, accurate. It's giving us, we've got set to 250 microseconds per division. That's the time it takes between it gets between one square. And its channel is 1 volt per division. So yeah, about 5 volts peak to peak, haven't we? 2.5, 5 volts peak to peak. It says VBW. BW is bandwidth limited. This scope is capable of 100 megahertz of response. Sometimes it cleans the scope up if we switch it down, so it's only got a response of 20 megahertz. More modern scopes these days will easily do 2, 3, 4, 5, 6, 700 megahertz, 1 gigahertz. They are much better than this. They are also considerably cheaper than this when it was new. It's got to be getting on for 20 years old now. It really has, if not older. But it's been, again, a very, very faithful friend. It was not cheap when I bought it, but it's a Tektronix. They cheap brands like Rigol, very nice scopes. They've got a bigger screen these days. There's several manufacturers that do inexpensive and very, very decent scopes. You see Keysight pushed everywhere on people's, on their channels, and they're great scopes. So what that does is voltage against time. There is another mode we use, if I go into the menu, which is somewhere, we can use maths, which is interesting. So we can do a fast Fourier transform. So if I set that for, say, hang on, sine wave frequency 20 kilohertz, we can see there that peak on the left hand side is our 20 kilohertz. If I switch to square, we all see we've got lots of harmonics. So it does us a sort of cheap spectrum analyzer for audio use. So yeah, there we are. There's a ramp waveform, bit of a pulse. So you can see the harmonics changing. So more analog scopes won't do that for you, but this one will. So yeah, there it is. Of course, we can trace data like we've seen with the ZX81 and the VIC-20. We can watch audio in audio circuits. We can see that. Yeah, I could just lash up a bit of audio. Have I got the ability to do that quickly? Let's just stop there. So there's the oscilloscope, useful for tracing a circuit through. Often manufacturers will give you photographs of oscilloscope traces, or artists' drawings of them, so you can follow a waveform through a circuit and try and get your head around what's going on. I will just mention one big disadvantage with that scope, and it's all to do with the scope probes. There they are, scope probes. I often break them. I've not been good with scope probes over the years. I'm hoping to treat these ones with a little more respect. This crocodile clip here is coupled back to the 3rd pin on your plug. It is a safety ground. Now, this gives us a big problem. So, for one thing, say, like when we were working on that Philips television set, if I'd have used this scope and I was running my set, especially off an isolation transformer, so it's not going to present so much of a shock hazard to me. The reason we do that is the set is no longer referenced to Earth, and therefore I am referenced to Earth because I'm stood on it. If I were to touch a live wire, obviously if the voltage was referenced to Earth, it would attempt to flow back through my body and I'd feel a shock. Let's try not to do that. So we're running it on an isolation transformer. Now this scope is plugged straight into the wall. That is not isolated. This means this is connected to our safety mains Earth. If I was to connect that to our chassis on our television set, that chassis is now referenced to Earth the same as I'm stood on. So now, if I were to receive, touch something carelessly or brush against something, that voltage is now referenced back to mains Earth, and I'm going to feel a shock. Be very careful of that. Also, if you're working on something that's mains powered, always isolate it and isolate the scope separately. There's another way around this. However, do not ever lift your scope Earth. It's a safety device. I've seen and argued with people over this over the years. You are removing a safety device. Don't do it, folks. Just understand that that is ground. Also, if you're putting that into a circuit and the circuit is not expecting that to be grounded, well, you're going to upset the operation of that circuit. That's why an oscilloscope, you do have to be a little bit careful about it. And also, you can create a ground loop with the scope, which will upset the measurements, possibly causing you some hum on audio, for example, because this is grounded. Don't lift the safety ground on your scope. Find another method of doing it. An isolation transformer is a quick way of safely breaking that earth contact. So you can do that if you wish. But yeah, don't do it. And the other problem with lifting an earth, especially on a modern scope such as this one, is normally there's a safety capacitor, an X or a Y class capacitor. Let me get that right. It's X, isn't it? Or is it Y? Can't remember. No, it's a Y class capacitor across it's a safety capacitor anyway, across the isolation barrier. And that will introduce a load of noise if you do it. I caught an apprentice of mine at a certain establishment many years ago. One of the old boys told her to lift the scope. And then I gave him a lecture on why he shouldn't. So don't do that, folks. There's always another method around it. And another method is to get yourself one of these weird looking things. You'll see this on the channel every now and again. This is a Fluke 123. It is of some vintage now. Oh, dropped my screwdriver. Never mind. I shall have to have a tidy up. This is a Fluke 123 industrial scope meter. It's long since superseded by something else now. But yeah, a great piece of equipment. If it wants to turn on, it will. There we go. No, not quite. I have to say the battery is very flat. And that's not helping us, is it? This wall wart is just a battery charger. The beauty of it is even though it's plugged into a wall wart, that wall wart is isolated. It's an isolation transformer. This has its own internal rechargeable battery. So these, it's just the same as a meter. There is no connection to Earth. It's a really useful scope. It's got a 20 megahertz bandwidth only. It has this oddball connector on the side here. And this is an infrared transmitter receiver. I've got a USB adapter that sort of sticks on there and it communicates via light to a PC. Again, no chance of any ground loops, you see. And you can print out the picture off the scope screen. You can see that on the website on a few different things. It was with a bit of software. It's very old and very cranky now. I have to say it's nowhere near as reliable as these. It's got some dead columns on the screen. And the battery is absolutely toasted these days. Not a common thing to see in the UK at all, but a useful thing when it's charged up. The other thing I will say about the display is it's not very bright when it is going. Ah, it was running beautifully when I did a dry run of this earlier. That's typical, isn't it? Anyway, that's something to consider. Any scope that's powered from batteries or through a wall wart, you know, should be fairly safe to use on mains board equipment as long as you know what you're doing with it. Always worth having a think before you connect something up, whether you're going to interfere with the circuit's operation or, you know, create yourself a safety hazard. Right, that's oscilloscopes. Other bits of kit you'll see me use. We have the Atlas DCA. These are from Peak. They're great. They do a load of different instruments in the same case. And this is a semiconductor component analyzer. So you hook your three-legged device onto these three hooks in any order you like. There we go. You push the test button and it goes, I'm analyzing. And it'll stop. It goes NPN silicon transistor. It's correct. We scroll down. It tells us the red is collector, green is base, blue is the emitter. Brilliant. Current gain's about an HFE of 16. It's a power transistor, sort of what we'd expect. Fairly low current gain. And it tested it with 250 milliamps. Base emitter voltage is 0.56. That correlates on what we had with the Fluke earlier. And a test current through the base of 4.85 milliamps. A leakage current of 0 milliamps. And we're back around to silicon transistor. It will test transistors. It will test diodes. The one criticism I have of it is it's not very good with germanium diodes. Silicon, fine. Field effect transistors, fine. Even most SCRs or triacs, it'll find. But yeah, not so good with germanium transistors. Sometimes it just says they're faulty and they're not an unknown device. This is a diode or diode junctions, cathode and anode. Forward voltage drop 0.64, 4.77 milliamps of test current. There we go. You know, that's a really simple, quick way. If you've done your test with your meter and you still want a bit more confidence in it, there you go, unknown or faulty component, it's just disconnected. That's a great thing. Then we move on to my arch nemesis, the horrible capacitor. You'll all know my hatred of this component and its unique ability to fail and really ruin our day. So we've got two devices we can use. This another Peak one. I think I bought these two on a deal. This is the Atlas LCR, LCR 40. It's getting on a bit now. I think both of these have been superseded. But these are great little instruments, pocket sized, run off a little sort of 12 volts car alarm kind of battery. So all you do is, again, you hook your component up. There is a warning here: avoid charges and voltages. So just discharge your capacitor before you do it. Analyzing in 5 seconds for 3. You can skip past that. Analyzing. Capacitance 713.5 microfarads. Interesting. That had it at 709, I think, didn't it? So yeah, we're in the ballpark. Capacitance. Scroll. Test frequency DC. If we'd used a smaller capacitor, it sort of ramps up the frequency it uses to attempt to measure it. So that's good. That's the only thing it gives us. The other thing it will test is inductors and resistors. Inductors, it obviously gives us a value in henries or microhenries or whatever, but it'll test a resistor just the same and just comes up with that value for you. 996.5 ohms. Near enough. So that is the Atlas LCR. L, inductance, capacitance and resistance. Great little instrument. Again, not very expensive to buy. There is a new capacitance one actually that does lists all the parameters of the capacitor, including the ESR. And we shall come on to ESR now with the Xingyan MESR 100 ESR meter. Yeah. So this is used to check ESR, which is the effective series resistance of this capacitor. And that's its ability to absorb charge, if you like. So you can have a capacitor that sort of measures all right for value, but its ESR is woeful. Now, the ESR of a modern capacitor, something of this value, so 680 microfarads, it should be practically nothing. So we attach our leads, and it will automatically range, and it says it's minus 50 ohms. Let's just zero the meter, shall we? There we go, we're zeroing. It's zeroed. Right, let's have another go at it. Yeah, almost no ohms, 0.03 of an ohm. So the lower that value, it's the better quality this capacitor is. You'll get some, as the lower the value of the capacitor is, so this is 680, so like a 4.7 will have a higher value. But if you're starting to get into the hundreds of ohms, your capacitor's really past its best. And I've seen people as well, you know, oh, why are you changing all the capacitors? Do you know what? When I'm inside a piece of equipment, if we want it back to spec, these things have a life expectancy. And yeah, they might still be all right today, but another 2 or 3 years' time, they might be shot. They're not expensive things to buy. The expensive bit is me doing the job, really. It's my time. So one out, all out, really. You know what I'm like. And you don't get, you know, you haven't got to worry about it then for a few more years with a bit of luck. There's a little chart on the bottom here which gives you values against sort of maximum expected ESRs. The voltage also, the voltage of the capacitor, so this is 25 volts, I think. Yeah, that also affects the ESR. So it sort of gives you a range of good values. You can sort of look it up on that table on the bottom there. But yeah, you sort of get a feel for these things. So that's all the sort of measuring instruments I use in a nutshell. There's obviously things that you can't see that are always off shot. And I tell you what, let's pick up a camera and just have a little look around the workshop at what we do have on the shelves. The shelves are an awful mess. As is most of the workshop, to be quite honest with you, but you'll get the idea. So sometimes things like the frequency counter and things have made an appearance on a handheld camera. Right, here we are. Right, okay, oh, there's the other camera. So, yeah, there is my bench power supply of some vintage. It's, yeah, a twin channel power supply, so we can have adjustable voltages on each side, adjustable current limit. Very nice. The Chinese make some of these now. They're very, very cheap. To be honest, if you've got something, this goes up to 3 amps per channel. If you've got something that does 3 amps, that's most of what you'll ever need. Dual channel one's nice to have, because obviously I can generate sort of plus and minus 15 volts if I need to there. Above that is a Rigol signal generator. That was generating our 20 kilohertz sine wave a minute ago. This is very posh. A friend of mine was disposing of this at a very, very sensible price, so I took his arm off. It's a great instrument, so I can sort of adjust the frequency, so I can go, I don't know, 1 hertz if I want. I can have a sine wave, square wave, ramp, pulse, noise. It'll generate a random noise signal, an arbitrary waveform which you need to program up, and I've never really bothered with. So that's a fairly sophisticated thing. We've got a keypad to enter some stuff in. We can do sweeps, we can modulate. We've got 2 outputs, and it'll also function as a counter. So it's a really great instrument, and I didn't pay £200 for that. It's a great thing. Here we have a very old TTI function generator. So this does sort of similar thing. It's a lot more analog in its option, and as you can see on the front, it says, caution, instrument outside of specifications, please refer to certificate. It came my way because it failed its calibration. And yeah, okay, if we were repairing aircraft or something like that, you could understand why you'd need that to be right. We're not. We're just generating a signal, you know, 452 hertz ish. There you go. We can select voltage, so we can change the amplitude, voltage peak to peak, or we can have a DC offset, so we can move the waveform about in position. So a useful little test set. Might not be the most accurate thing in the world, but you know, if we're just generating 700 hertz there, you know, if we're doing 2 kilohertz or something, we can generate that. I've largely superseded this instrument by the Rygold because it's so much better, but you know, occasionally it comes in. And above that is its best mate and brother, the TTI TF830 1.3 gigahertz universal counter. Now, there's also had a sticker on it to say it had failed calibration, and that's how it came my way. I have to say, I've had that on a 10 megahertz standard, and it's pretty good. I'd be happy with it, so I don't know what their calibration standard was too, but this didn't cut the mustard. So that will, yeah, count up to sort of 1.3 gigahertz in steps. So if we want a frequency measurement, we've got that there. Oh, that reminds me, the yellow Fluke does measure frequency, and it does hertz as well, and percentage of duty cycle. It's a clever instrument, but yeah. And there next to it is an RF frequency generator, a DA band for fixing and aligning radios. It's not very accurate at all. That scale on there is rubbish. Normally I'll couple it into the counter there, so we can actually see where we are. You can modulate it. I'll just move that out of the way. You see, this shelf has just gained rubbish over the years, Loctite and goo and all manner of stuff. So that's great for aligning our radio receivers and things. Going up another shelf. That's the workshop speaker. Look, there's the clock. That's a power supply I built when I was a kid. Behind it, 12 volts at, well, I think it'll muster a couple of 3 amps. There's a workshop television set. Now this is there is a TTI True RMS portable multimeter up there that I never use. Programmable. It's very, very good. It just takes up too much bench space. It's a bench instrument and I don't have the space. So maybe when I move, we'll get to use that. Underneath that is another thing that I repaired. It's a Polar T1500 fault indicator. Looks like an oscilloscope. It draws patterns depending on what's connected to it. So it's quite an interesting instrument. I might do something like that. There's a PAL television generator up in the corner. And right in the corner over there is the valve tester, which comes out occasionally. There we have it. It's all good fun. Oh, there is a Quantec over there. That's a distortion analyzer, and it's also quite an accurate signal generator. It's also got an oscilloscope on it, but the display is really damaged on it. It's got a lot of pixels missing. Cal soldering stations and my copy Haku. Yeah, it's a hot air gun. It actually works very well for a little copy. For fetching off larger surface mount things. That's the workshop in a nutshell, really. I should mention that thing over there, big grey thing with the meters on it, that is a variable isolated power supply. It's good for about 1.5 amps. I built it many moons ago. So yeah, you can see there we can vary the voltage a bit. It's a bit scratchy in its old age. It really does need taken apart and given a bit of a service. There's a current meter. I think it's 0 to 2 amps. There's 2 switches on the other end, and they provide 6.3 volts for valve heaters. It's great for radios and things like that. Not so good for repairing television sets because it really is on the limit of the current it'll provide. In which case, I generally use this thing here, which is connected to the variac. So this is an isolation transformer. There's a variac there hiding down the side of the Quantec, and then feeds this ancient load box with volts and an ammeter on it, which we then connect our bits and pieces to. So that is again another isolated variable mains supply. Yeah. Right. Is there anything else I ought to mention? Do you know, I think there is. I will just come to one final idea of testing, and that is testing chips. Now, if you've been on the website, you'll see this come up occasionally. RS 212691. Lab property, do not remove. Yeah, it's an IC tester, and it has no battery in it. And I'll tell you for why. Yeah, because I pinched the battery out of it the other night. I must order some more. You plonk your IC in there. You select the type. On here, it comes up with 1,000,000 ohm. It's been shown on the website a few times. You push the test button, and it tells you whether that chip is good or bad. You won't buy one of these anymore, which is a bit of a shame. There are various chip testers you can buy for doing vintage computing kit. And that's all very well and good, but you can really do yourself a favour and buy yourself one of these. Like we saw on the VIC-20, on the VIC-20 repair we've just done. This we used to blow the proms. Now, not only will it test and program EPROMs, but it's also got a section in the software that allows you to test hundreds and hundreds of different types of logic chip. You of course need to have a Windows PC. I think there's a version of the software to run Mac. My operating system of choice is Linux, so I have to say, I've always used the proprietary Windows software. It's a dual boot computer, so I overcome my phobia of Windows and just get on with life. So yeah, I load that up, and it's great. You can test hundreds and hundreds of different types of logic. It's no good for things like SIDS and VICs and things like that. There are specific chip testers you can buy for that sort of thing, but it will test lots of them. I ought to see whether it does static and dynamic RAMs. I don't know, but there we are. So that is the test gear we've sort of amassed over the years. The most important one, every time, it's going to be a multimeter. It's the instrument we use more than anything else. Second most important, for me, it's got to be the oscilloscope, I think. The luxury items to have are things like the programmer, but this is also, you know, a tool as well as a test instrument. These are great for just simple quick tests, yes, no answer almost, to allow you make an informed decision. ESR meter, well, I used to use it a lot back in the day. Now I just chuck them away and change them because, you know, they're pennies. Let's move on in life. But yeah, multimeter, got to be the most important. So there you go. Test equipment. There's loads of it. The things I probably could do without, I could do without the signal generators a lot of the time. You can generate audio signals, for example, with your laptop or your mobile phone for next to no money. You've got to be careful what you connect your mobile phone to. You don't want to go damaging that. But yeah, there we go. Test equipment in a nutshell. Whatever you're doing, obviously play safely. Think about things like working on mains equipment with an oscilloscope. It can be an absolute minefield. Just think for a moment. And if you've any doubt, don't do it. I need all the viewers and readers I can get. I've always said that. So, you know, the safest connection to the mains is no connection at all. So, yeah, that's it, really. Anyway, thanks for watching. I hope Mr. Unknown or Mrs. Unknown or Miss Unknown on the website, that's answered a few of your questions. Yeah, test equipment. Great stuff. Couldn't do without it. Thanks for watching. Like, subscribe, do all that other rubbish. And I will see you very soon here on Doz's Television Workshop. Cheerio.